Good day, and thank you for the opportunity for myself and Kaylee van Wyhe to present our combined research focused on understanding the impact of inflammation on cognition outcomes in the context of perinatal acquired HIV. To understand the impact of therapy and chronic inflammation on cognitive outcomes, our research draws on two disciplines, neuropsychology and immunology. Cognitive outcomes were evaluated at 7 and 9 years of age, and immunological data was generated as part of a follow-up study from the well-known Children with HIV Early Antiretroviral Therapy, or more commonly known as the SHARE trial. Despite antiretroviral therapy, many display impaired cognition and behavioral difficulties. Key domains of impairment include psychomotor functioning, attention deficits, and executive functions. Several studies have highlighted that HIV infection, particularly perinatal acquisition, is associated with a higher risk of cognitive impairment in children. These cognitive deficits can have long-term consequences affecting educational attainment, social functioning, and overall quality of life. However, the exact mechanisms driving these cognitive impairments are not fully understood. The role of inflammatory cytokines and chemokines have been implicated in driving cognitive impairment in both adult and child populations. Some signature pathways have been described in adults as depicted on this slide, however less within children of schooling age. Within the SHARE cohort, we have previously documented a degree of immune dysregulation at a pre-adolescent age of 8 years in various immunological compartments despite early therapy and biological suppression. We have also noted chronic inflammation linked to early gut damage, mainly driven by the monocyte macrophage pathway. Compared to HIV-negative controls and HIV-exposed uninfected controls, perinatally infected children display a distinct pattern of cytokines and chemokines that are driving chronic inflammation even after long-term viral suppression. Following correlation analysis, evaluating neurocognitive outcomes, we observed key predictors related to early immunological, virological, and clinical parameters. We have also documented the role of early immune responses in changing brain morphology within the same cohort. These findings has led us to explore the research question: what is the impact of early inflammation, antiretroviral therapy, and viral suppression on cognitive outcomes at 7 and 9 years of age in children with perinatal HIV? I will now hand over to Kaylee to take us through the second part of our presentation.
Thank you, Selena. Good day, everyone. I will provide a brief overview of the 7 and 9 year cognitive outcome study. Following that, we'll delve into the methodology of our current study, which aims to investigate the correlation between immunological markers and cognitive outcomes. We are aware that the SHARE trial found that early ART initiation significantly reduced mortality and HIV disease progression. However, HIV may continue to affect the brain and the body throughout critical developmental stages of childhood and adolescence. We investigated cognitive outcomes at 7 and 9 years of age in children from the SHARE neurodevelopmental substudy. Our study population comprised of the 3 HIV-positive groups from the SHARE trial. Comparison groups comprised of children HIV-exposed uninfected and HIV-unexposed uninfected. We used an observational longitudinal design. Data were collected between May 2012 and December 2017. Children living with HIV had regular 3-monthly adherence visits and clinical evaluations. HIV-uninfected participants had 6 monthly clinical assessments. Participants were administered a comprehensive test battery at age 7 and 9 years. These are tests commonly used in pediatric neuropsychological assessment with strong psychometric properties and proven utility across different cultural and language contexts. The cognitive test assessed domains of visual motor integration, information processing, attention, receptive language, fine motor dexterity, and executive functioning. Caregivers were administered a study-specific medical sociodemographic questionnaire. Most caregivers were the children's biological mothers. 90% of children living with HIV were virally suppressed, with CD4 percentages above 35% at both time points. 76% of children were in age-appropriate school grades. Analysis of both the 7 and 9-year data detected no significant between-group differences for viral load, CD4%, weight, height, and art compliance. Looking at the cognitive outcomes, the observed data suggests three things. Firstly, that children living with HIV experience deficits in executive functioning and auditory working memory, regardless of the ART treatment plan. Research shows that deficits in executive functioning might indicate difficulties in planning, monitoring, and decision-making. Therefore, these children may underachieve educationally. Secondly, regardless of group assignment, children living with HIV performed equivalently to controls, except in the case of the two cognitive domains mentioned previously. And lastly, that cognitive recovery is possible. For example, deficits that may exist at 7, such as fine motor dexterity, appear to resolve at 9. What does this mean? Although neurocognitive developmental trajectories for treatment groups and controls were largely similar, all ART-treated HIV-positive children, regardless of their treatment arm, remain at risk for cognitive deficits over early school ages. By combining our data sets, Shalina and I were able to investigate the relationship between immune biomarkers and cognitive outcomes in the HIV-infected children. This data allowed us to identify potential markers or predictors of cognitive impairment at 7 and 9 years of age in the SHEER cohort. Back to you, Shalina.
Thank you, Kaylee. Focusing on the key aims and objectives of this research, our aim was to delineate the impact of early immunological and clinical outcomes on cognitive parameters at 7 and 9 years of age in perinatally infected children. We really wanted to understand the association between early immunological insults and pre-adolescent cognitive outcomes. We also wanted to identify key immunological biomarkers of HIV-associated cognitive outcomes amongst school-aged children living with HIV from the SHEER trial. To briefly take you through our study design, this was a longitudinal study focused on follow-up research of the SHEER trial participants subjected to various therapy arms as mentioned earlier. Immunological parameters were measured shortly after birth. We termed this baseline, and then 2 to 3 years after therapy initiation and at 8 years of age. We also evaluated total HIV-1 DNA within a subset, and various clinical parameters were assessed for associations to immunological, biological, and cognitive outcomes. We employed both Luminex multiplex assays as well as ELISAs to evaluate over 40 immunological biomarkers spanning characteristics for pro- and anti-inflammatory, T-cell associated as well as monocyte macrophage associated biomarkers and measures for mucosal immunity and gut permeability. For our statistical analysis, we mainly employed Spearman correlation analysis and verified these with Pearson correlation rank tests and linear regression analysis. Briefly looking at baseline demographic characteristics for our study population, we characterized these into 4 study groups based on delayed, early initiated and continuous therapy as well as interruption arms. We'd like to draw your attention to key differences related to lower birth weight and lower CD4 percentages at birth within the group with early initiated continuous therapy. A longer time to viral suppression in the group interrupted at 40 weeks can also be noted. So what did we observe? With analysis focused on associations between baseline immune biomarkers and 7 and 9 year cognition parameters, we present association data by use of visual heat maps. Looking at data on the left presenting 7-year cognition outcomes, we see various clusters, but of particular importance I'd like to draw your attention to the cluster in the bottom left corner. Here we see strong associations between key inflammatory biomarkers including IL-2, IP-10, interferon gamma, soluble CD163, often implicated in neuroinflammation, IL-18, and the mucosal biomarker LBP. These biomarkers have been associated with various cognitive impairments including visual spatial reasoning, problem solving, mental processing, fine motor dexterity, and attention deficits. At 9 years of age, to the right of the slide, we observe even more associations as noted by the expanded box in the corner, highlighted with the red color, with specific cytokine and chemokines including GCSF and PDGF, again associated with attention and fine motor dexterity. We also observe strong negative associations between IL-1RA and inflammatory protein CRP with impulsivity and mental processing. Following 2 to 3 years on therapy, we observed the interplay of similar patterns of immune biomarkers at 7 and 9 years of age. Again, we note more neuroimmune associations at 9 years of age compared to 7 years. These key immune biomarkers at play include IL-6, MCP-1, CD40 ligand, RANTES, and soluble CD14. These biomarkers were particularly associated with auditory working memory, attention deficits, and receptive language domains. And at 9 years of age, commission errors or impulsivity, as well as attention being the key domains affected by the inflammatory immune response. At 8 years of age, with long-term viral suppression and reconstituted CD4 counts, we observed key biomarkers, again including IL-2, IL-12, IL-17A, and interferon alpha, influencing cognitive parameters for receptive language, visual motor integration, fine motor dexterity, mental processing, as well as overall learning. Lastly, drawing on the associations between clinical and biological parameters, we observed strong associations between gestation time and longitudinal CD4 percentage with attention scores at 7 years. Longitudinal CD4 percentage also negatively associated with impulsivity parameters at 9 years of age. With the use of a multidimensional scaling plot presented in this slide, we see an association of total cell-associated DNA, a putative biomarker for the HIV reservoir, on various cognitive parameters. We are yet to delineate and explore this data point further.
Thank you, Shalina. Despite early ART initiation and viral suppression, inflammatory insults affected later cognitive performance. Our data suggests that early immunological and clinical parameters may predict cognitive outcomes during later childhood in children living with HIV. This knowledge can aid in the early identification of at-risk individuals and facilitate the development of targeted interventions to mitigate cognitive deficits. Additionally, understanding the specific immune pathways involved in neuroinflammation can guide the development of novel therapeutic strategies aimed at reducing neurocognitive impairment in this population. We want to express our heartfelt appreciation to the dedicated staff at FAMCRU as well as the exceptional parents and children who participated in our study.